Okay, welcome back, everyone. So, just a brief recap of where we were. We were dealing with the second main example of my lectures, which is this modified Bessel equation for this function g. And I also told you that there is an integrable representation for this function g, which is, you can see as a toy model of a matrix integral or of a path integral. And of course, there is a choice of contour that plays an important role. But we started by ignoring the integral representation and looking at the differential equation alone. And I started by telling you, okay, remembering what happened with the Euler series example, we want to start with an ansatz which might capture all the possible solutions to this equation. And in fact, this ansatz, which contains a formal series multiplied by something that is not a formal series because it doesn't have a Taylor expansion at infinity. By plugging these ansatz into the differential equation and checking order by order in Z, we found that first a quadratic equation for what I call the instanton action, which had two solutions, obviously. One is 0 and the other one is 3/2. So we can immediately say that there are two solutions with very different properties, one which I call the perturbative sector and the other non-perturbative sector. One is captured by a standard formal series and the other is not. And I think this is a good point to make a little digression on the integral representation, because this links very much to some things that Bertrand told you a couple of days ago. So let me call this guy here minus the potential of this exponential integral. So v of x is okay. And now let's try to see what are the allowed contours of integrations that we can take in this integral. So for the moment, we take Z real and positive, and so we distinguish the complex plane for x, which is the variable we are integrating over, in sectors where these areas here are the areas in which the real part of the potential is smaller than 0. So real of v of x smaller than 0, which means they are not allowed for us. We cannot go to infinity along those regions. And the rest is real part of v of x greater than 0. So as Bertrand showed you a couple of days ago, you can immediately see 4 possible paths that you can follow to integrate. And they are not linearly independent, as it was shown. You have 3 independent ones. And in fact, well, there is this problem as a Z2 symmetry because we can always, the potential is symmetric. So actually, it turns out that 2 of these paths give the same contribution. So it's as if we had 2 independent paths. So how do we compute an integral like this? First of all, we look at the potential. Again, we are in Z real and positive. You look at the shape of the potential. And you see it does something like this. So you have 3 saddles. One is what I will call the perturbative saddle, because essentially its height is 0, so the potential is 0 at that saddle. And therefore, when you do a steepest descent integral along a path passing from the perturbative saddle, it will not have something like e to the minus az, because it's as if a is 0. The other two saddles are at x equals to plus minus square root of 6z, and the value of the potential there, I will call them x plus minus. The value of the potential there is 3/2 z, which is precisely what we expected looking at what we found from the differential equation. So we could have, in principle, ignored completely that there was a differential equation underlying this problem and just looked at the integral representation. We would have found exactly the same two sectors, an instanton sector associated with these two saddles and a perturbative sector associated with the perturbative saddle, right? And then when we want to do carry out this integral doing a steepest descent technique, essentially we choose a saddle. In this case, we have the three saddles here. Let me erase some stuff. You choose a saddle and you integrate along the steepest descent path, which, for example, now I have to be careful about what I do. So I will have to put myself with give a slightly imaginary part to z. So arg of z greater than 0. You check what the steepest descent contour is for the perturbative saddle. It's something like this. It goes to infinity like this. Okay? And then you check for the non-perturbative saddles what kind of steepest descent contours, and they are like this. Well, let me use another color maybe. This is terrible. Blue. And then you have this passing through the other perturbative saddle. So why did I give a little imaginary part to z? Because if I now look at what happens very similar when I give it a small negative imaginary part. The steepest descent contour passing through the perturbative saddle changes drastically. It flips. That's something like this, while the other two remain essentially the same. Okay. So it's as if going from crossing the positive real axis, when z crosses the positive real axis, we have something discontinuous happening. And if we called gamma 0 the steepest descent path passing from the perturbative saddle, gamma minus this one and gamma plus this one, it's as if by crossing the positive real axis, gamma 0 goes to gamma 0. I think it's plus gamma plus minus gamma minus. I might have messed up some signs, but it probably depends on the orientation. Yeah, I think so. So the steepest descent path jumped, and this is, we will see that this is will be encoded at the level of the solutions of the differential equation in a jump of the resummation of this formal power series. So this is a visualization of the Stokes phenomenon at the level of the integration contours of this quartic integral. Another little comment, and of course, if you now do the same thing around, instead of argument of z close to 0, we do it close to pi, which is another place where we expect a Stokes phenomenon to happen. We will see something analogous, but this time it will be the gamma plus at pi. It's gamma plus that jumps and gamma minus 2. While gamma 0 stays essentially the same. There's no discontinuity. So, and these jumps will be precisely encoded in the discussion I will make on the differential equation. And a final comment on the x-plane. We can also visualize the Stokes phenomenon as some array in the complex plane at which the asymptotic behavior of our object changes. So, for example, in the positive real axis, a solution like this one. So e to the minus 3/2, sorry, yeah. The non-perturbative solution is exponentially suppressed with respect to the perturbative solution. On the opposite side, in the negative real axis, the non-perturbative solution is exponentially enhanced with respect to the perturbative solution. So a way of visualizing Stokes lines, which are the lines in the complex planes across which we have jumps of the kind that I showed you. You can also visualize them as lines across which the asymptotics of the object you're considering starts to change. And just a little bit of terminology more that you might find in the literature. What I just described to you are Stokes lines. There are also anti-Stokes lines, which are lines at which essentially all the sectors contribute to the same order. So in our case, it would be at arg z equal to pi halves and 3/2 pi. There you will see that, you see immediately that the instant on x, this term here will be of the form 3/2 I absolute value of z. So it's neither exponentially enhanced or suppressed with respect to the perturbative sector. It's just an oscillating term. So at the anti-Stokes lines, the perturbative and the non-perturbative are of the same magnitude in some sense. Okay, so after this digression on the integral representation, I have to make another little digression, but I don't want to tell you too many details because we will not need them. But just to tell you a little bit more about what a trans-series is, because I will use this word a lot, and you will see this word a lot in the literature on Resurgence. And I already told you that this kind of object here for a different than from 0 contains something that is not captured by a Taylor expansion at infinity, which is this e to the minus az. And this is the kind of contribution that I call a non-perturbative contribution. So if I want to write the most general solution to this equation, it will be something like zero. What I'm doing is very trivial. I'm just taking a linear combination of the two solutions I found, which I labeled G0 and G1, where G0 is just some formal power series that I call F tilde 0. And 0 and G1 sorry, G1 is yes, sure. Yeah, of course, and I will, yeah. In fact, there is a closed form. So we are very lucky. Typically, when you have a differential equation and an integral representation, you know that you have a lot of control over your problem. And in fact, I can write not only, of course, the first thing you do is plug this into the differential equation, solve order by order, and get a recursion on the coefficients. So it's not necessarily true that you will be able to find a closed form for the coefficients, but in this case we can. So I will write it down, and in fact everything will be very explicit for this example. So you see that the most general solution is not a formal power series. It's something that is a formal power series plus something that is not a formal power series. And this is what we call a trans series. And well, this little digression on trans series that I will make now is mostly taken from the Dorigoni reference that I showed you at the beginning. And in fact, Dorigoni takes it from a very nice review by Edgar, which is called Trans Series from Beginners. Edgar. For beginners. Which contains much more detail than what I'm going to show you right now, but we don't need many details about trans series. In fact, this is the kind of object you will always see in my lectures, something like formal power series attached to some e to the minus z something, okay? But in general, we define, and you're probably not going to like this definition because it's sort of circular in a sense. So a log-free transmonomial which is the building block of a trans series, something like e to the minus az, for example. We define it as a symbol of the form z to the a, e to the t, where a is some real number, and t is a purely large log-free trans series. So you see what I meant when I said trans series. It was a circular definition because I'm defining the building blocks of trans series using trans series. And then I define a log-free trans series as a formal sum of transmonomial. of the form. Yeah, sorry, let's call it this G. Dj, where this guy here is a transmonomial. So, if you're not happy with this definition, there is a non-circular one in this review by Edgar. But for our purposes, it's enough. I just want to emphasize that it's going to be something that does not have logarithms, so that's why it's log-free, and something that can have, in principle, through the circularity of this definition, you can have something like e to the e to the e to the e of stuff. We will focus on height 1 transseries, which are transseries in which you can only apply the exponentiation once, essentially. Okay? So you don't, it's, for the purpose of these lectures, you don't need to know a lot about transseries. It's just, yeah. Yeah.
This condition of log-free doesn't mean because, when you have a fundamental solution, for example, maximum monotony theory, then the structure of your fundamental solution for the system is very special. For example, the first function in this fundamental system. Is it the same?
Okay. I don't have a... So, let me put it this way. So, I will be able, through Resurgence, to show you the monodromy of this solution, of the general solution. But yeah. But in general, so I also want to stress that this log-free condition is kind of special to the examples I'm showing you in very interesting cases, and in fact, typically in string theory and matrix models, you will have logarithms in the transseries, but it's nothing particularly scary. So now that we are done with these digressions, I want to give you the explicit forms of these coefficients, which we can obtain. In fact, you can obtain it in two different ways. You can obtain it by plugging the ansatz into the transseries and solving the recursion for the coefficients, but you can also obtain them using the integral representation and doing the saddle point approximation along some steepest descent contour. Okay, so coefficients takes this form. Factorial 2 to the 6n 2n factorial n factorial. And these ones are the same up to a minus 1 to the n. So you immediately recognize the factorial growth of the coefficients because we have essentially 4 factorials at the top and 3 at the bottom. You see that there is an exponential growth dictated by the instanton action, which is also something that is expected. Oh, sorry. And of course, yeah, they are defined up to some up to the first coefficient. Okay, but these two guys, alpha 0, 0, alpha 0, 1, we can actually fix them using the integral representation. So by performing the integral to the lowest order, we obtain these two values, which I will not be very important, but it's just to let you know that they can be fixed. Okay. Now we can do what we do best, which is Borel transforming it, right? We just divide by n factorial and see. Sorry, the first coefficients. You can just do the integral in the saddle point approximation, stop at the first order, and that's your result. So, but I mean, of course, if I had put here some alpha, some constant alpha, this g of z would have still solved my differential equation. So it's not really important. What is really important is the ratio between the two, but not really their value. So we can perform the Borel transforms, and in fact, then you can take your favorite computing software and you plug in the Borel transformed coefficient, the Borel transformed power series, and ask, for example, Mathematica to resum it, and it will spit out some well-known functions. So, Borel transform of 0 in the variable s. Of course, it will have the unit of the convolution product, because our power series have a constant term. But then the holomorphic germ at the origin is given by something that is very well known, because it's a hypergeometric function, 2s thirds. And the same goes for the formal power series associated to the non-perturbative sector. Changes a little bit because of the different coefficient. And we are very lucky because we know a lot about these functions. In fact, you can check on your favorite book on famous functions, or again, you can use Mathematica and look at what kind of singularities these guys have. And this will give us the singularities in the Borel plane of the formal series we started from. So we know that a 2f1 hypergeometric ABC. Sorry? Oh, sorry. Yeah, my bad. There's a minus here, which is crucial, of course. This kind of hypergeometric has a singularity at z equals to 1. Therefore, these two have, this guy has a singularity at s equals to 3/2. This one has minus 3/2. So again, the instant on action dictates the position of the singularity in the Borel plane. And now, if I want to look how these guys behave near the singularity, remember that earlier I told you a lot about simple singularities and how we would like to stay in that space of functions. Well, it turns out that they have exactly the kind of behavior we like. There's some coefficient. So we have the simple pole, as is expected. Oh, and let me call, sorry, these two germs, I will give them the usual name, phi hat of 0, and this one, phi hat of 1. They're just the Borel transforms of phi tilde 0 and phi tilde 1. And you see something very neat happening here. So they both have simple singularities, which is already pretty cool, because that's what we want. But also, attached to their singularities, so attached to the singularity of the perturbative sector is the Borel transform of the non-perturbative sector. And vice versa. And plus, this plus whole means the regular part, which we don't care about. So, let me repeat. I have computed the Borel transform of the formal power series associated to the perturbative sector. I look at the singularity in the Borel plane, which is only one, and it's simple. And attached to it, I find the Borel transform of the non-perturbative sector. And the same goes for the non-perturbative sector. I find the Borel transform of the perturbative formal power series attached to the singularity.
So you make 3 half.
Yeah, A is 3/2. Yeah. So no, A is just, yeah, sorry. Yeah, let me remove this essentially. So my definition of A is 3/2. Yeah, exactly. So as I said, the Borel transform of the perturbative sector has a singularity at 3/2. The Borel transform of the non-perturbative has a singularity at -3/2. Okay? So A and minus A. Okay? And this is actually what gave the name to Resurgence, the fact that you see one sector reappearing or resurging in the singularities of the other sector. Okay? And this is nice because in principle we could have been very naive in our ansatz for solving the differential equation. We could have found only a formal power series that solved our differential equation. And even if we had completely missed that there was a non-perturbative sector, we would have found it in the singularity in the Borel plane of the perturbative sector. Okay? So let me repeat. We were smart in writing down the formal series, but in principle I could have given you just these coefficients without telling you where they came from, and told you, okay, study this formal power series and tell me what you find in it. And so even if I had known knowledge only of the perturbative sector, I would have found the non-perturbative sector contained in the singularity in the Borel plane of the perturbative sector, okay? So, and to turn this into using the language of alien operators that I introduced this morning, now, of course, our situation is that the Borel plane is very simple. We have for phi 0 perturbative sector, we have only a singularity at 3/2. And therefore, it's not like we have many choices of alien operators. We have only one singularity and essentially the path gamma that goes from the origin to the singularity. Okay? So the dependence on gamma of the alien operator is trivial. So I can write down this. Yeah. The alien operator for the singularity in A acting on the perturbative sector is twice the Borel transform of the non-perturbative sector. Sorry. and the alien derivative, sorry, the alien operator acting at minus a of the non-perturbative sector is minus 1 the perturbative sector. Now, let me spend a few words on these numbers 2 and minus 1, because they seem quite arbitrary at the moment. And in fact, these numbers are called the Stokes constants. Or sometimes holomorphic invariants. They are not easy to compute in general. So in this case, we have a lot of control over the whole problem because, well, as I told you, we have a differential equation and an integral representation, and this gives us a lot of control. And in fact, we are able to do the Borel transform, resum it. We have some nice functions that we know about in the Borel plane. And therefore, we are able to say, okay, the coefficient in front of this singularity is 2, the coefficient in front of this singularity is minus 1. But in general, these are numbers that are not easy to compute. And one often has to rely on numerical methods to compute them. So is everything clear so far? Are there any questions? Now, of course, our final goal is always to resum these divergent power series. And to do so, we have to do the Laplace transform along some direction. In our case, we only have 2 forbidden directions. It's the positive real line for the perturbative sector and the negative real line for the non-perturbative sector, because that's where the singularities are. Therefore, let me do this for this is the Borel plane of the perturbative sector, phi hat of 0. Singularity here. 2 possible lateral resummations. And in fact, I think I didn't use it before, but I will use the notation S of some angle, well, S of some angle theta, curly S of some angle theta, to call the resummation along some direction. So this includes, this acts on formal power series in Z, and it does both Borel, it's the Laplace along theta of the Borel of phi tilde, okay? So it's the whole resummation procedure. You first Borel and then Laplace along some direction. This is my notation for this whole resummation procedure. Okay, so we have some resummation along a ray that is slightly above the real line, which I call S minus, and the one that is just below. And when I want to compute the difference between, now I'm interested in knowing, since, okay, we have discovered that essentially our resummation will jump when we cross the positive real line. So we want to know by how much it jumps, and this will give us an idea of the monodromy of the solution of our differential equation. So the difference between the 2 resummations is again the same thing that I did before in the Euler example. So taking the difference means, okay, we change the direction of this. and then we continue. But in the earlier example, we only had a simple pole, so it was just a residue computation. Here, we have a logarithmic cut, so in general, we're doing something like this. This is S plus minus S minus. And the result is actually pretty simple because we know essentially these two contours of integrations with opposite directions just above and just below the real line are computing the discontinuity of the logarithmic cut. So, and the discontinuity of the logarithmic cut is encoded in the Borel transform of the non-perturbative sector. So this turns out to be, with very simple manipulations and a translation of the variable integration, 0, 1 plus the resummation along 0 of the non-perturbative sector times e to the minus za. This will depend on z. Okay, so for the resummation along 0, along the positive real axis of the non-perturbative sector, we don't have to worry because the singularity of the Borel transform of the non-perturbative sector is in the negative real axis. So this does not need to be defined slightly above or slightly below. You can define it on the real axis. And we find that the result is very similar to what we obtained in the earlier example. We have a contribution that is non-perturbative in this sense, but there's much more structure to it because this is a legitimate function in Z. Okay, and same goes for non-perturbative. Something very similar, but now, of course, this was the Stokes coefficient associated to the singularity of the perturbative sector, and will get the Stokes coefficient associated to the singularity of the non-perturbative sector. And sorry, now I almost made a mistake because now the discontinuity for the non-perturbative sector is going to be for the resummation along direction pi and not 0. So this is pi plus, pi minus, let's call it, and this is 0 plus, 0 minus. And this is the resummation along pi of this. Sorry? Yeah, sorry. So here we got a non-trivial difference between the two resummations, the two lateral resummations close to the positive real axis. We got a difference that is this guy here because we had a singularity on the positive real axis. This guy here does not have a singularity in the positive real axis, so if I do the same thing, I get 0. But now it has a singularity in the negative real axis. So the two, if I were to draw the same thing for minus, now I want to do the same thing, but along the negative real axis. So singularity here, resummation along okay. This is okay, and there is an operator that is convenient to introduce and that will play also a role later, which really encodes in a very compact way the monodromy of the solution to our differential equation, which is the Stokes automorphism, which is defined in this way. Simply resummation, the lateral resummation to the right is equal to the lateral resummation to the left combined with this Stokes automorphism along the direction theta. So this might seem a bit obscure as a definition, but in the end, it's just saying to us that since this, we can call the Stokes automorphism the identity plus the discontinuity along the direction theta. So essentially, this Stokes automorphism is computing for us the discontinuity across a given direction. It will be 0 for all directions in which we don't have singularities, and then it will be non-zero on where we have singularities, or if you will, along Stokes lines. So we say that the Stokes automorphism acting on some phi tilde is again phi tilde if phi tilde is what we call a resurgence constant. Okay. So I think this example is quite instructive because it shows simple resurgent functions appearing in a kind of straightforward way, and you see immediately how the implication that resurgence is telling us that the various sectors of a given function we are computing talk to each other through the singularities in the Borel plane. And now, just a final word on the monodromy of this system. So, by making use of these two computations we did, we essentially get that now, if we apply the lateral Borel resummation just to the right of the positive real axis to our full trans-series, recall that this is what I called it. Let me write down again what G was. So our trans-series was packaging together both the non-perturbative and the perturbative solutions with some parameters sigma 0 and sigma 1. Now, what does, we want to do the lateral Borel resummation along the direction 0 plus, and this will be equal to 0 minus, but with difference parameters sigma 0 and sigma 1, because sigma 0 stays the same. No, sorry. Yeah, right. Sigma 0 stays the same, but sigma 1 goes to sigma 1 plus 2 sigma 0. And I hope it's clear why this happens, because if we apply the lateral Borel resummation to the whole trans-series and compare it with the lateral Borel resummation just above the real axis of the whole trans-series, the whole trans-series gets an extra piece, which is this 2 times the Borel resummation of the non-perturbative sector. So by crossing the positive real axis, sigma 1 jumps by 2 sigma 0. And a very similar thing happens along the pi direction. But this time it's the sigma 0 that jumps, or the first trans-series parameter that jumps. And it jumps by minus sigma 1 because of this computation we just did. Okay, so now, given this knowledge, we can essentially say everything about the monodromy of the most general solution to this differential equation. Because remember, we had the Stokes automorphism, which was encoding for us the jumps across each Stokes line. And when we move around the origin twice, now let's put ourselves in the Z plane. And imagine we start from some point in the complex Z plane and we move around twice. This was once, twice. What we did was apply the Stokes automorphism in the direction pi and in the direction 0 twice. And we see that under this, it's kind of an easy exercise to check that given these relations that I wrote here, we can tell immediately what the action of this operator does, and it sends sigma, the pair sigma 0, sigma 1 to minus sigma 0, minus sigma 1. So going twice around the complex plane changes the sign of our transeries parameters. Then it's obvious to see that going 4 times around the complex plane sends our transeries back to itself. So it's a way of seeing the monodromy of our solution. Essentially, our solution lives in a multi-sheeted surface, and by rotating many times around the origin, we go back to itself. Another little comment. Yeah. Yeah, sure. Sorry?
So like the sigma theta, or I don't know, sigma?
Yeah, it's a sort of curly sigma.
It's the identity
Plus the discontinuity along the ray theta. So essentially, it's identity. Yeah, exactly. I think so. Yeah, that's the. It's the identity plus resummation sigma plus minus resummation sigma minus. This is how you can picture it. Yeah, I'm just defining it like this. Yeah, if you want, this can be a definition. To be completely rigorous, this is not the definition. The definition is given in terms of alien derivatives, but I will get there in a second. But yeah, you can for these simple cases in which you have only one singularity in the Borel plane, this is an appropriate definition of the Stokes automorphism, and it's just a way of capturing the discontinuity across a Stokes line.
Just from like the Stokes constants, right? That it's like the work are just reapplying the automorphism at a time, so you can just see it by.
Yeah, exactly. That's the thing. Each time you cross a Stokes line, your transeries parameters sigma 0 and sigma 1 jump by a certain amount, and by checking how they jump after several turns around the origin, you compute the monodromy of your solution. Of course, there is a way, I don't think I have time to do that, but there is a way of seeing exactly this kind of monodromy appearing from the little discussion on integration contours that I did before. So in that case too, you saw the steepest descent contours jump when we cross Stokes lines. And by taking care in an accurate way of those jumps, you recover the same exact monodromy. Okay. Now I think I'm a little short on time. How much do I? No, I have 1 more hour, right? Okay. Great. So yeah, I can then make a little comment on asymptotics too. So I told you before that as we move, for example, when we start here in the Z plane, when we are on the positive real axis, the non-perturbative sector is exponentially suppressed with respect to the perturbative, because it goes like e to the minus 3/2 z. And then when we move around in the complex plane, the asymptotics change for our solution. And this can be seen very, very neatly by this jumping of Stokes trans-series parameters. So imagine we start from sigma 0 equals to 1 and sigma 1 equals to 0. So we start from a purely perturbative trans-series. And we start from argument of z slightly below the slightly negative. So we are starting slightly below the positive real axis. It's here. Now, the first thing that happens when we start to move counterclockwise in the complex plane is we cross the positive real axis. So something happens immediately. The non-perturbative sector turns on, even if it was off. So we cross R plus, and we get sigma 0 equals to 1, sigma 1 equals to 2. Okay, so we have acquired a non-perturbative contribution just by moving around in the complex plane. When we get here on arg of z equals pi halves, we see immediately exactly the oscillating behavior that I was telling you about. So in that direction, the contribution of the non-perturbative sector is of the form minus I 3/2 absolute value of z, and so oscillatory behavior. And this is something that you will see, for example, also if you try to apply this kind of reasoning to the Airy function, okay? The Airy function that you plot through Mathematica, for example, is something like this, some exponential decay and then some oscillations. And this is a very similar phenomenon. This is a Stokes phenomenon. You're just, this change of asymptotics from exponential decay to oscillation is exactly what is happening in this case here. Okay. Now, this example, which was already kind of rich of structure, is still very simple because, and the simplicity of this example is due to the fact that we are dealing with a linear differential equation. When we start to move to nonlinear problems, things obviously become much more complicated. And a way of seeing this happen is, for example, by as I said, this example was computing essentially a partition function for us, okay? If we wanted to compute the corresponding free energy, so the logarithm of the partition function, you would find that it also satisfies a differential equation, but it's not linear anymore. And therefore, the structure becomes much more complicated. And in particular, what you typically get in nonlinear examples, and I will show you one at some point if, yeah, time permitting. What happens in nonlinear examples is that you get infinite arrays of singularities in the Borel plane, or even more commonly, lattices of singularities. So let me show you what I mean by this. When you try to solve I'm not going to write down the nonlinear differential equation corresponding to the logarithm of g. But if you plug in the transseries ansatz that we wrote before, so you plug in the full transseries into the logarithm and try to expand order by order in e to the minus ZA, you will see that the neutron series that is encoded by this new object, right? Sigma 0, sigma 1, oh, yeah. Sigma 0, sigma 1. The neutron series will contain an infinite tower of terms of the form minus nza, where n belongs to the natural numbers. This means at the level of the singularities that you expect in the Borel plane, that if you had started from something that had a single singularity in some point of the complex plane, this kind of transseries, which will be a sum over n of terms of this kind, will have an infinite tower of singularities in the Borel plane. And even more commonly, what happens is that you have two distinct instanton actions, A1 and A2, and the typical transseries that you will find is going to be a sum over two integers, e to the minus, sorry, n A1 plus m A2 times z, which means that, for example, if these are, this is A1 and A2, they will generate for you a lattice of singularities. And this might seem already still manageable, and it is. But one very important difference with respect to what we were doing earlier is that if now we want to choose to resum in some directions, if we encounter a singularity in that direction, we automatically encounter infinitely many of them, okay? So we need to find ways of managing these kind of situations. For example, I mean, the Stokes automorphism that I defined earlier will have to deal with a sum over infinite singularities. So let's try to formalize this a little bit. So consider the situation in which, in a given direction, I have an array of singularities, okay? Omega 1, omega 2, dot, 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 up to some omega that I want to reach, for example, with my alien operator, okay? As I told you before, the alien operator depends on the path you choose to reach the singularity. In particular, in a situation like this one, you can choose to organize your paths in the following way. You follow the direction, and then you avoid the singularities to the left or to the right, okay? Until you reach the singularity you wanted to reach. Now, this means that a path like this, which I call gamma epsilon, I can label it essentially by this epsilon, which is a set of choices, epsilon 1, epsilon r, where the epsilon i's take values in plus minus. Okay, so essentially the plus choice is when I avoid the singularity by going to the right. The minus choice is when I avoid the singularity by going to the left. And therefore I call the alien operator associated to this kind of path A omega gamma epsilon. And there is a privileged alien operator that I can construct by combining these elements, these building blocks here, which is the alien derivative, which is simply a weighted average over all these possible choices. So the alien derivative, which I call delta of omega, which is not to be confused with the loop insertion operator, but there's no ambiguity here. It's just the sum over all possible choices, left and right, times some combinatoric factor, which essentially gives us the weighted average. So P of epsilon is the number of pluses in epsilon, and Q of epsilon is the number of minuses in epsilon, gamma epsilon omega. So we're taking, let me repeat what we are doing. We have a lot of singularities, a long array that leads us to a singularity omega that we want to measure somehow. And we have a certain number of possible paths to choose how to avoid all those singularities. If I sum over all these alien operators which are associated to each of these possible paths, weighted by a combinatorial coefficient that enforces a weighted average over all the possible choices, I get the alien derivative. And I will show you in a minute why it's a derivative, which is very important. Bear in mind that in the literature you will find also, for example, this guy here, delta omega plus, which is instead obtained by taking only the path that avoids all singularities to the right. Also, this guy plays a role in alien calculus, but I will not spend too much time on this, also because this is not a derivative. It's not a derivative in the sense that it doesn't have a Leibniz rule. So I will show you the Leibniz rule for the alien derivative. Delta plus would require a modification of the Leibniz rule, which is not particularly useful in our case. So just a little example with 3 singularities to fix the ideas. Yes. We have omega 1, omega 2, omega 3. If we want to compute the alien derivative at omega 1, this is very simple because I don't have to avoid any other singularity. So it's just the alien operator at omega 1. Then if I want to compute the derivative, the alien derivative, this delta plus is the alien operator that I associated to the path that only has pluses. Yeah, sorry. I want the alien derivative at omega 2. Now I have 2 choices. I can do either this or that. And so it will be weighted average omega 2 of gamma plus 1/2 omega 2 gamma minus. For the third singularity, I have even more choices. 1/3 omega 3 gamma plus plus 1/3 gamma minus 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 plus. Okay? So we are taking into account all possible choices, all to the right, all to the left, 1 and 1, with different coefficients dictated by this factor here. Now, how is this a derivative? There is a theorem that tells us that if I take a couple of simple resurgent formal power series, they don't necessarily have the same set of singularities. So one will have singularities in omega prime, for example, and the other at omega prime prime. Then the alien derivative of the product of the two formal power series is the alien derivative of the first times the second plus okay. So this is standard Leibniz rule. This is why this is a derivative. And also, of course, I could have replaced everything with their Borel plane counterparts. So replacing tildes by hats. But this, of course, amounts also to replacing the Cauchy product with the convolution. And the same goes. Now, another very important theorem is the following. And this is actually quite easy to show if you go to the Borel plane, but I want to enunciate it in the Z plane. Sorry? Yeah, sorry. So, as I was saying, another theorem is about the alien derivative of the derivative of a formal power series, simple resurgent formal power series. And it tells us that it is the derivative with respect to Z of the alien derivative of the formal power series almost exactly, in the sense that there is a little correction here. So it almost commutes with the standard derivation with respect to the Z variable, up to a piece that it's quite easy to take care of, because we can easily introduce a new alien derivative called the dotted alien derivative, which is defined as e to the minus omega z, the alien derivative. And it's very easy to check that now this new dotted alien derivative commutes with the standard derivative with respect to z. So let me call it dotted. Okay, so another little comment I would like to make is that, in fact, if one wants to do things rigorously, and that's what, for example, Suzanne does in his book, we would define the Stokes automorphism in terms of the alien derivative. So the Stokes automorphism that I showed you before in the case of one simple singularity, which is a very privileged case because it's very simple, the Stokes automorphism that I defined as essentially the discontinuity across a Stokes line of our resummation, that's not the most rigorous definition of the Stokes automorphism. The way to define it actually would be in terms of the alien derivative. So the Stokes automorphism along some direction theta is defined as the exponential, the sum So let me explain what I mean by this. Well, first of all, the exponential of the alien derivative means what you might guess it means. It's just the sum over n over 1 over n factorial So this is what this notation means. And what do I mean by this omega theta? It's just that I'm trying to check how my resummation procedure is discontinuous across some direction theta. And if it's discontinuous, it's because we have in the Borel plane along theta one, possibly many singularities, omega 1, omega 2, omega 3, and so on. And this omega theta is the set of singularities along the direction theta in the Borel plane. Okay? Could be infinite, yeah. That's why it's not super rigorous to define the Stokes automorphism as the discontinuity when you have infinitely many singularities, because you have to show that you are able to essentially sum over infinitely many singularities. So this is the rigorous definition of the Stokes automorphism. And then in some cases you can show that indeed it is equal to the identity plus the discontinuity across the direction theta. But this is between commas, because you have to show it case by case that this is true. And this is funny because in the physics literature, this is given the definition as the definition of the Stokes automorphism, and this is given as the definition of the alien derivative. So the alien derivative is defined as the logarithm of the Stokes automorphism. Sorry? Yeah, then it's in fact I think I have it as an example. For one singularity, this is super easy to show that the two are equivalent. And in fact, well, I erased the example I did before, but when you have only one singularity, say you have a singularity here, yeah, singularity here at A, of my formal power series, which is a simple resurgent power series. So when I act with my alien derivative A on my formal power series, I will find some other simple resurgent function, which we know will belong to simp omega minus A. Okay, so it will not have a singularity at A anymore because my space of singularities has been shifted by A, right? So if I act twice with the alien derivative on my original function, it will be 0. So, sorry, let me write this. Because psi doesn't have a singularity at A. So it's very simple to now develop this exponential, because it just gives identity plus S1, which is some constant, the Stokes constant associated to the particular singularity we are considering, e to the minus za delta A of phi tilde, which is exactly the result that we found in the example I showed you before. So because this guy here now is phi tilde, and earlier for us this was phi 0, the perturbative guy, and this guy was the non-perturbative guy, and we had found exactly the same result. So the discontinuity is essentially given by the Stokes coefficient times the other sector. Okay. So I would like now to move to the final example, because so far, okay, we have found some nice structure. We have found a way of encoding the discontinuity across some Stokes line using the alien derivative. We have shown that the alien derivative is truly a derivative and that it commutes with a standard derivative with respect to z. But okay, what is the use of this? So hopefully in the next example, you will appreciate the beauty of this structure. Example 3. Riccati equation. So let's consider the following nonlinear order 1 ODE. D of phi to z Okay. So this is very reminiscent of the Euler example. So the very first example I gave you. In fact, if we forget about the nonlinear term, it's almost exactly the same in the sense that we would get, let's forget about it for a second. You would get, the Borel transform would be 1 over S minus A. So, well, A is just some complex number for the moment. I will take it real and positive in a minute. But so you see that this would give us a very simple Borel transform, just a simple pole at A, nothing special. But it's the nonlinearity that makes it much more complicated. So we don't have any nice statement like this one. And in fact, well, if we try to solve, to throw in a formal power series ansatz into this equation, we find that, for example, we are not even able to write down a closed formula for the coefficients. We get something like n factorial for some extra coefficients Cn which depend on A and which can be determined recursively. Now, this is not particularly important. It's just to emphasize that typically what we have to deal with are situations in which we are not even able to write down a closed form for the coefficients. So how can we, for example, write down the Borel transform of this and study its singularities and the monodromy of the general solution of such an equation? Well, the thing is, well, when you have a differential equation, you can still try to prove some results about its Borel transform, about the Borel transform of its solution. And in fact, the people were able to prove that this series is Gevrey-1 type. Which is not super obvious because you have to also understand the growth of this coefficient Cn. But maybe this is the easy part. The non-trivial part that people were able to prove is that it has only simple singularities. There it is. At A, 2A, 3A, and so on. So an infinite array of singularities, which for now we will just restrict ourselves to A, positive and real, so they will all be on the positive real axis, okay? And then if you want to throw in a transseries ansatz for such an equation, you convince immediately yourself that this singularity structure in the Borel plane is reflected also by the transseries ansatz, in the sense that something as simple as the previous example is not possible. So you cannot get a closed form for just a perturbative plus non-perturbative kind of ansatz. Here you will have infinitely many non-perturbative sectors, and the transseries will get a form of this kind. I will write it capital phi, depending on one parameter sigma. Sigma to the n. And A, Z. So you see that we have, it's similar to what we had before, but now we have an infinite tower of non-perturbative contributions labeled by this, but a certain power of the transseries parameter. And of course, for each non-perturbative contribution, we have a formal power series. Okay, so of this problem, what do we know so far? Just that the position of the singularities, the fact that they are simple singularities, which is very important to us, the fact that, of course, the Stokes lines are at 0 and pi, like before. And then we are going to discover something very, very nice about alien calculus, which is the following statement. We know that our transseries, capital phi, solves some nonlinear differential equation. And we know that the alien derivative, the dotted alien derivative, commutes with the standard derivative. This implies that the dotted alien derivative of the transseries that solves our nonlinear equation will solve a linear problem. And I will show you immediately why this is the case. So, my statement is that dotted alien derivative at some point k of A, where k is an integer of z sigma, solves a linear ODE. What is this linear ODE? Well, no, this has to do with the fact that delta Ka dot. No, it would be the same even for higher order. Sorry, not higher order in the derivative, but higher power of phi. And this is due to the Leibniz rule of the alien derivative. So let me show you precisely what happens here. Imagine I act on both sides In fact, it will be linear and homogeneous. I hacked on both sides of my equation with the dotted alien derivative at the point Ka. I get something like d of dz equals to 0. So I've only used the fact that the dotted alien derivative commutes with the standard derivative and the Leibniz rule for the dotted alien derivative. So you see that this is extremely general. I could have had 3 here, and I would have had a square here, but no substantial change. It's still linear in the dotted alien derivative. But there's more, and there's the real juice of this kind of computation, which is the fact that we also have that the derivative with respect to the transseries parameter sigma commutes with the standard derivative. And so I can play the same game, exactly the same game, and act with the derivative with respect to the transseries parameter on the left and on the right, and obtain exactly the same linear homogeneous equation. Oh, sorry, sigma. So we have something very interesting happening here. We have that the alien derivative at the point Ka, dotted alien derivative acting on our transseries capital phi, and the standard derivative with respect to the transseries parameter sigma acting again on the transseries phi solve the same linear homogeneous differential equation. So they must be proportional to each other. Up to some constant, which can depend on sigma, of course, but it cannot depend on anything else. And what we have just obtained is the bridge equation. It's called the bridge equation because it's essentially a bridge between alien calculus, such the alien derivative, and standard calculus, which is a standard derivative with respect to sigma. Okay? And this is we have put ourselves in a kind of a simple situation here, but you can write bridge equations for many problems, and they simplify things a lot. Oh, I'm out of time, I think. Ah, no, 20 minutes, okay. Perfect. So how do we use the bridge equation? First of all, let's look at now both sides of the bridge equation. So let's call it, well, it's fine. On the left-hand side of the bridge equation, we have the dotted alien derivative acting on our transseries. And remember, we had written an explicit formula for the transseries here. So we know how the alien derivative acts. So this, with respect to the original transseries, this factor of e to the minus k a z comes from the definition of the alien derivative, of the dotted alien derivative. I don't know if you remember. I don't think it's on the blackboard anymore. The dotted alien derivative at some point omega was defined as e to the minus omega z, the standard alien derivative. Okay, so this extra e to the minus k a z comes from the dotted alien derivative at the point Ka. And now we have delta, this usual undotted alien derivative acting on. For the moment, well, so remember that I told you that we have singularities at A, 2A, 3A, and so on. Sorry? Yeah, I mean, we want to measure all these singularities. So I'm leaving kappa unspecified, but kappa is an integer. So it's measuring the, well, it's actually a natural number. For the moment, let's put it integer because these are the singularities of the perturbative sector, but the non-perturbative sectors will have shifted singularities. So they will have also possibly negative minus A, minus 2A, and so on. So for the moment, I leave it unspecified. It's just an. Yeah, exactly. Yeah, if you want, yes, precisely. So for every one of these guys here, I write an equation. So this is the left-hand side. We have just done nothing particularly interesting. The right-hand side, again, we know how to take the derivative with respect to sigma. It's sigma enters in a very simple way in our transseries. So right-hand side is sk of sigma So I've done nothing particularly interesting. I've taken the derivative of sigma to the n, which gives me n sigma to the n minus 1, multiplied by this proportionality constant that appeared in the bridge equation. And there's that. Now we want to match powers of sigma on both sides of the equation, right? And also powers of e to the minus az. This already tells us that, I mean, on the left-hand side, we clearly have only positive powers of sigma. So this fixes for us the dependence on sigma of this constant sk up to something. So the sk's must have the following form. Sigma to the m for some coefficients belonging to C. Oh, sorry, this is obviously wrong. And now also, I've told you that the dotted alien derivative adds for us a factor of e to the minus k as az. So in order to have a matching of both powers of sigma and powers of e to the minus az, we also have to impose, we have a very strong constraint on this coefficient. And in fact, this gives us some sk constant sigma to the 1 minus k. So this kills this sum, essentially, the constraint that the power of sigma matches the power of e to the minus az has a very stringent constraint on the shape of this proportionality constant in the bridge equation. And now, again, we match term by term, and we obtain the following results that you can check easily. So, for k greater than 1, the alien derivative of the formal power series associated to the nth instanton sector is 0. And this doesn't mean that this sector doesn't have a singularity at Ka, by the way. It just means that the alien derivative is 0. I showed you before. Okay, so it's a constant. It's a function of sigma, so it's a constant from the point of view of the derivative with respect to z. That was the important part. But it could have any dependence on sigma a priori. But then, by imposing essentially that the left-hand side and the right-hand side have the same structure in terms of powers of sigma and powers of e to the minus az, which might seem not super clear by just looking at these two lines, but I swear if you sit down and and do it, it's super simple to see that this kind of requirement is the only way of having the power of e to the minus az match the power. Well, they do not match, but the combination, the combination must match from the left-hand side to the right-hand side. Okay, so well, yeah, if it's not obvious, just trust me on this, and you can verify it yourself. And also, so from very similar considerations, we get this kind of constraint on the alien derivatives themselves. Okay, smaller or equal to 1. This is very simple. If you think about it, this is very simple to what was happening in the example number 2, in which we only had two sectors, 0 and 1. Here we have a generalization to infinitely many sectors. They are all related to each other through alien derivatives. Okay, the n plus k sector appears as the alien derivative of the nth sector at the Ka point. Okay. And again, this might not be super obvious, but as soon as you start playing with these two equations and matching term by term, you realize this is the only possibility. And then this helps us a lot because we can use essentially this consideration to study the monodromy of the general solution of this equation without even having been able to write down an explicit Borel transform, or we are not even able to write down a closed form for the coefficients here. But thanks to the bridge equation and to the properties of the alien derivative, we can essentially say a lot about the monodromy of the general solution, of the general transseries solution. And this is obtained in the following way. And I will do for you, because of, well, my time is very limited, I will do for you just I will show you what happens when we cross the positive real line. Remember that the Stokes lines are at 0 and pi, so I will show you what happens across one of them. And it's quite simple, actually. It takes me probably 2 minutes, because remember the definition of the Stokes automorphism, that for us gives us the discontinuity across a certain direction. So direction 0 is the exponential. this would be the definition in our case. Remember what I had told you before? The definition earlier was along some direction theta is the exponential sum for all omegas, all singularities on the ray theta of the e to the minus omega z delta omega. And this is exactly what we are doing. But now all our singularities are on the positive real axis. They have all the same spacing dictated by this integer k. So, and now essentially, we just use the following result that we obtained, which is this here. Sorry. Yeah. This result here. And remember that we have fixed this. So this is actually sk sigma 1 minus k. So this guy here. Sorry. Right. Yeah. Sorry, I forgot a little step here. So remember also what I had wrote here, another direct consequence of the bridge equation, that for all k's greater than 1, these alien derivatives are 0. So essentially, only the k equals to 1 term survives. So it's just e to the minus az delta a, which is equal now using the bridge equation a1 derivative with respect to sigma. And now we apply this operator here. I just use the bridge equation here. So this guy here is the dotted alien derivative, which is equivalent to multiplying by S1 and taking the derivative with respect to sigma. So we now apply this Stokes automorphism to our trans-series solution, sigma z. And we know very well what this operator does. It's just a translation by A1. Sorry, S1. Yeah. It's just a translation by S1, which is there was a much longer and difficult way of obtaining this result. You see that using the bridge equation, we obtained it immediately. So we know, even though there's a lot we don't know about this problem, because there's very little we can compute explicitly, we know that the jump when we cross the positive real axis of our trans series is by S1. Now, of course, S1 is what I had called earlier a Stokes coefficient. So it's something that is not easy to compute explicitly. In many cases, as I said, you can get very good numerical results for them, but yeah, it's you would need some extra input to have something like an explicit formula for S1. So I still have 10 minutes, right? So well, yeah, I'm basically done. I don't want to overwhelm you with. I hope. Are there any questions regarding the brief? Well, so for example, in example number 2 that I did, In that case, everything was very much under control. Here, one way would be, for example, to you can, for example, there are ways of approximating the Borel transform of a formal power series. So imagine you are able to generate many of these numbers. Okay, so many of these of the coefficients of our formal power series. So you don't have a closed formula for them, but you can generate many of them using Mathematica, for example. Then you're able, of course, to Borel transform whatever you have obtained. And there's a way called that uses Padé approximants that approximates for you the Borel transform in the Borel plane. And the good thing about Padé approximants is that they also approximate for you the singularities in the Borel plane. So that is a way of getting some idea of how the singularities in the Borel plane are. Another way is by using some large order relations that if I have 5 minutes, I will tell you what they are. Unfortunately, I will not be able to show you a proof of why these large order relations happen. But in any case, the short answer is that typically we cannot compute Stokes coefficients. So we need to have a lot of control over the problem. Yeah, exactly. If you have integrability, if you have an integral representation, sorry. Yeah, in some cases. No, not really, not really. Not always. I mean, in the examples, yeah. In the example I showed you, they were integers, but they can be very, very complicated. I mean, they can be transcendental and everything. I mean, it's not. Unfortunately, there's no general theory for computing Stokes numbers, which are I would say the hardest thing to computing when dealing with resurgence.
So, like a typical example with standard 1 and 2 is you reapply 4 times and you get back the same.
Yeah.
It's transcendental.
Yeah, typically, I mean, well, let me think. The thing is, first of all, you don't necessarily, I mean, that example that I showed you that showed that the monodromy is relatively simple. So after 4 turns, you go back to where you started. You don't necessarily need to go back somewhere when you turn around the order. It can just be essentially like the logarithm kind of situation. But yeah, unfortunately, these Stokes coefficients are a very hard problem in the resurgence. Sorry? They would, if I had time, I would have showed you also what happens when you cross the pi Stokes line. In that case, they would play a role. But for the positive real line, they don't play a role. But this is, a feature of this particular problem or class of problems, because what I did was quite general for this kind of transseries. Well, it's almost my time, so yeah, no, probably it's not a good idea to start introducing more stuff, but yeah, I think I will conclude here.
Say the definition of this was not rigorous when there is an infinite number of
Yeah.
you replace that by an infinite number of terms.
Yeah, right. But that's a definition, let's say. Yeah. So I think so. What is not rigorous is essentially this equality. So if I say that this is my definition of the Stokes automorphism using the alien derivative. So it was the exponential sum over omega belonging to omega theta of the dotted alien derivative. If I take this as my definition, then what is non-trivial to prove is the equality sigma theta equals the identity plus the discontinuity somehow. So, yeah. Well, this infinite sum means essentially that, I mean, you have infinitely many singularities along a. Yeah. Yeah, of course. Yeah. Yeah, no, in a sense, I mean, you can always define this like this, but then whether it makes sense as an object, yeah, it's not clear. But I think Suzanne, for example, has some very precise statements on this. Yeah. 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 Yeah, they would. So yeah, in that case, you would have an infinite number of sectors popping up when you compute the discontinuity. But that's also, in fact, the surprising thing is actually that only the first one contributes when you cross the positive real axis, because a priori you expect all singularities to play a role when you're crossing a Stokes line, because you have, there's no good a priori reason why only one of them should play a role and the others should somehow cancel. So in fact, I think the more expectable result is the other one, in which all the SKs play a role.
Is that the singularities are just like hidden?
No, I didn't. It was not obvious at all by looking at the differential equation. It's just a result that I think it was proved by Dalabert and Pham. So sometimes just by you can prove results, but just by looking at the differential equation without even knowing precisely what the Borel transform is. You can say something about the distribution of singularities and stuff like that. In this case, they proved that they were simple singularities and that they were all at those multiples of A. But yeah, it's I didn't show at all why this is the case. Yeah, no, it's not obvious at all. Given a general, you're asking, given a general, let's say, Gevrey 1 formal series, if there is something like that. Yeah, there are definitely. But you mean, so conditions on the coefficients of the series, for example? What would you? Okay, on the differential equation, probably there is some literature, but I don't have a precise answer for that. But yeah, definitely you would need more than just, give me a sequence of number and I give you the distribution of singularities in the Borel plane. But if you give me a differential equation, yeah, I'm pretty sure there is some literature on how the zeros of the Borel transform distribute, but yeah, I cannot recommend you anything off the top of my head. Thank you.